Hi everybody, I am in week number 2 of our course Moodle page, and I wanted to just quickly give you a video for an explanation of these materials I've posted for the Euler Approximation Lab. The very first thing I want you to know is it is not due this week, it is due next week. I want to give you access to it a couple days early so that if anybody wants to start working on it this weekend, they can, and they don't have to wait for me to open up week number 3 on Monday. All of these materials are posted at the end of week number 2, but I'm also going to have the submission link posted in week number 3 so that you realize it's due next Sunday, January 29th. So the first thing I need you to do is take a look at the instructions. Each of you has been assigned a different differential equation and initial condition and target value to approximate. And there's a link here where you can find your assigned differential equation, initial condition, and target value. And the target value is exactly 1 unit away from your initial condition. So if I told you what's happening at x equals 0, then I want you to estimate what's happening at x equals 1. If I told you what's happening at x equals 1, then I want you to estimate what's happening at x equals 2. So your initial condition and your target value are always 1 unit away from each other. And we know one of them, but we don't know the other. You're going to use this information in your Euler template. So for part 1, I want you to open this Euler template and you're going to make a copy and save it to your Google Drive and give it a very specific name. So first let's open it. You're not going to have edit access to this. What you need to do is go to File, Make a Copy, and then you're going to name it with your name, and this is Euler Part 1. If you have folders, you can save it in a particular folder. If not, you can just save it in your one big Google Drive folder. So I'm going to make a copy of this, and it will reopen, but now it is editable. So what I want you to do is enter your differential equation and your initial condition. So let's say my differential equation is dy dx equals 2x minus y. And I was told that y of 1 is equal to 3. We're trying to find y of 2. And once we figure out that value, it's going to go here. That's our final answer for the approximation. So to plug in to this formula, the whole reason I want you to do this with a Google Sheet is because on part 2, we're going to be doing step size of 100th, and we're going to be performing our Euler approximation 100 times. The nice thing about electronic spreadsheets is that once you establish a pattern within your cells, you can just copy it and drag it, and the Excel sheet is smart enough to know to copy those formulas into the other cells. So really, we only need to fill in the first few lines of this table, and we'll be able to drag the rest of it. So x sub n, this is our first x value, which is in your initial condition inside the parentheses. Mine is 1. And my y sub n is what that first value is equal to, which is 3. So basically what I've said here is when x is 1, y is 3. That's your initial condition. dy dx is a formula. It's 2 times your x value minus your y value. But you don't want to calculate that by hand. What we want to do is use the location of those values to tell our spreadsheet a formula. Anytime we type a formula into the spreadsheet, we start with an equal sign. And I want Google Sheets to do this calculation for me. I want it to do 2 times my x value and then subtract my y value. And I get a first dy dx of -1. For part 1 here, our step size is just 1/10. To get the next x value, all you're going to do is take your first x value and add your step size to it. But to get the next y value, if you remember when you did this by hand in your homework last week, you are going to start at your first y value, and then you are going to follow your slope, but only for the distance of your step size. So I used my y value and then added together the product of my slope and my step size. And it gives me approximate new y value. Again, from last week, remember these values at the end of the table are now the starting values for the next iteration. So you don't want to type those in by hand, which I just did. What we want to do is actually say that this value should always equal this value. And this y value should always equal this value. And then dy dx, again, we're going to calculate it. It's 2 times the x value minus the y value. And we have a step size of 0.1. And the new x value is the old x value plus the step size. And if you noticed, when I first went into that box and hit the equals, it tried to guess the formula I was using, and it actually guessed it correctly. I like to fill in several of these rows on my own. That way I know I've established the pattern and not allowed Google Sheets to make too many guesses. And then our next y value, remember, is our most recent y value, and we're going to follow our slope, but only for the distance of our step size. So those get multiplied. And we have a new x value and a new y value to transfer down. New x value, new y value. And I'm gonna fill in the rest of this third row here. And then everything from row 1 and row 2 right now is based on formulas. So that should be enough information for Google Sheets to recognize the formulas and allow me to just drag and fill in the entire rest of the chart really quickly. So really quickly, one more dy dx, we know it's going to equal 2 times the y value, or excuse me, 2 times the x value, and then minus the y value. And the y value is in this cell. Step size of 0.1. The new x value is the old x value plus the step size. And then the new y value is the old y value plus, we're going to follow our slope for the step size. I do not highlight the first row because the first row has some hard-coded values. We typed the number 1 in and we typed the number 3 in those first 2 boxes. And I want Google Sheets to recognize every cell as a calculated value. So I'm only going to highlight the second and the third row in there, and then I'm going to drag that blue box down to the end, and it should fill in all the rest of the values for us. So look at this. Our Euler template has approximated that when x is 2, y is 3.04603532. This is what we're looking for. We're looking for y of 2, and we found it to be 3. And we can actually, if you want to, we can even just say it equals what's in that box. So we just have to get those first couple rows in. And instead of using variables or instead of using hard-coded numbers, we type in a formula and we reference where the values are in the chart for that formula. For part 2, we're going to do this again. The difference, though, is we're going to use a step size of 100th, and you are going to drag this table down until it gets to, again, y of 2, but it's going to take 100 steps to get there. And you might get a similar value, and you might not get a similar value. Every single differential equation is different. Euler's approximation is just an approximation, and it's highly dependent on the step size. So don't get too frustrated if in part 2, when you do this again, you get a completely different answer than you got for part 1. But this is all I want you to do for part 1. You're just going to fill in this table, and we have an approximate y of 2 value based on our differential equation and an initial condition. For the second part, we're going to go ahead and make a copy of this one. The difference is I'm going to call it Euler Part 2. And I'm going to go in and I'm going to change the step size to 100th. And I need to do that for all of these. And you notice when we do that, we don't have the approximation for when x equals 2 is anymore. We have the approximation for x equals 1.1 because we've only done 10 steps and each step was only a length of 100th. So we've only gone a tenth of a unit. So what we need to do, I'm going to delete this because it's in the way. We need to extend this table all the way down to about cell number 100-ish. Let's see where we get to. So on this, it's 106 is where we hit 2. We really don't need any of the rest of this stuff. So when I do step values of only 100th, I get an approximation of 3.09809.724. And we will want to highlight that cell or maybe move it up here. So it's equal to this value. So when I look at those two, 3.09809, 3.04603, they're very similar. They're definitely not the same, but they're very similar. So that's good. The final part of the lab is to work out that differential equation by hand. In section 2.3, we learn how to solve linear differential equations using an integrating factor, the mu value. So all of these differential equations that I've provided are linear differential equations, and you need to solve them by hand. At first, you're going to get a general solution. The general solution still has the arbitrary constant c in it. But since we have an initial condition, we can use that initial condition and plug it into our general solution, and that's going to solve for that arbitrary constant, and we can rewrite our general solution with the arbitrary constant replaced. That gives us a particular solution. It gives us one particular solution that satisfies that one particular initial condition. And once we have that particular solution, we can just enter in the value we're trying to calculate. So I was trying to calculate in my charts y of 2. So the x value is 2, and we're trying to figure out which y value goes with it. So all I have to do now in my particular solution is to plug in an x value of 2 and see what y value I get back. So we've got 3 different answers for kind of the same thing. We've got a weak approximation, a stronger approximation, and then an exact value. And what I want you to do is to compare them and see how close they came to one another. They might be really close, they might be really far apart. Which approximate value from your charts came closer to your exact value, and why do you think it's closer? What part of the problem, or what did we change that could make the approximation better, whether it was part 1 or part 2? There is a grading rubric listed, so you know exactly how it's going to be graded. You've got 2 Euler charts to turn in. You want to have only a minimum number of hard-coded values. If you remember back, I only hard-coded the H value got typed in manually, and the very first x and y values got typed in. Everything else after that is typed in as an equation. It's equal to something from a different formula or from a different cell. So you want to have the absolute minimum hard-coded values. We want to use formulas and then drag the formulas to copy them to fill in the table. Otherwise, it's just going to take way too long. So all those fields are clearly filled in. Your solution is clearly stated. Don't just give me your chart and leave me to assume you know what the chart is saying. You need to tell me what your approximate solution is. That's going to be worth half of your grade. 50 points is to get those charts completed correctly and fully. And then the other 50 points is going to be based on working out the problem by hand and writing your short reflection. So working out the problem by hand, you need to show all of your steps, and you need to correctly find and identify your particular solution and your target value. It needs to be neat and legible. That's going to be worth 40 points, and then your reflection is going to be worth 10 points. Now that you've seen how quickly that chart can be created, this probably won't take you too long to do, but you need to make sure that you're turning 3 files in. You're going to have 2 chart files to turn in, and then you're probably going to have a separate PDF file that shows your handwork solution and your reflection written out. So you have 3 files to turn in. And you can get started on this right away, and you can turn in the files one at a time. It's completely up to you. The submission link will allow you to enter multiple parts.